So how do we measure isotopic abundances when we can't count how many atoms of an isotope we've got in a sample directly? How do we measure isotopic masses when we don't have any kind of analytical balances in the lab that can weigh masses that small? Well, we use a technique called mass spectrometry, and I'd like you to know the pieces, the steps, in how it's done. A lot of these instruments you can find on Compton Hall in our labs. Alright, the first thing you do is you atomize your sample. Let's suppose we have a sample of chlorine, okay? And we've got two isotopes in there. We've got chlorine 35 and we've got chlorine 37, which I'll draw a slightly different color and a slightly different size. First thing we got to do is get our sample into the gaseous state. So you're going to have to vaporize your sample. If it's liquid, you can put it on something hot. Then we pass it through something that is going to ionize it. Now, one way to do that is with a filament like this. A hot filament like you used to see in old style incandescent bulbs spits out electrons, and those electrons can knock electrons out of the gas atoms that pass by. So when these pass through the filament, or if you don't want to use a filament, you can use an electron beam, kind of like a cathode ray, and hit the atoms with that and knock some of their electrons out. Now these things that come out the other side are no longer just the gas atoms. They now have a positive charge on them. Now we put a positive charge on them so that we can steer them around. Because if you have a positive charge, you want to find something negative to go towards. So we're going to have a plate here. And it's going to have a narrow slit cut in it. And it's going to have a negative charge on it. Now when these positive ions see that negatively charged slit, they're going to accelerate towards it. And some of them are going to hit the outside of the slit, and that's the end of their journey. But some of them are going to squeeze through the slit. And what we're doing here is two things. Thing one is get a very tight beam of these things, because we made it pass through a slit. And thing two is we get them moving fast. So this negative slit accelerates and focuses. The beam betters our sample. Now these still have positive charges on them, so let me write the little pluses in there. The next thing we're going to do is pass it through a magnet. So if we've got a big magnet here, let's see. Not the best magnet. We have seen that when you have charged particles that are moving very fast, and we've got the charged particles moving very fast now, a magnet will exert force on them. They will bend, their trajectory will bend. And it turns out that if you've got very light ones, they will be bent in the magnetic field quite a lot. And if you've got very heavy ones, they will be bent not so much. So let me put the right ones on. What's that? Yeah. these light ones are going to go down here, and this heavy one is going to go up here. So the magnet effectively is separating ions of different masses. And then finally over here what we can have is a strip of film or something, a detector in modern instruments. And these things are going to hit the film in different places. And they're going to expose the film. And the darker the film is, the more ions of this type are. Now we can read how dark the film is very carefully, and we can see that it's 3 times as dark here as it is here. And that will give us the abundance. That will tell us that there are 3 of these for every one of those. And by looking at where it hits along the film, we can tell what the mass is going to be. So from this film strip, you can read the abundance as the darkness of the spot. You can read the mass as the position along the film. Now in modern instruments, they've got a bank of sensors here that are going to translate this and make a graph for you. Let me draw the graph. You will see on the computer screen something with abundance up here. And usually the machine will put charge to mass ratio down there, or mass to charge ratio. But the way these instruments are usually set up, the charge of the ions is always +1. So you can essentially say that what you see along the x-axis is the mass in U. And from reading along the film strip, we can see that we get a peak, a very sharp peak at 35U. And we're going to get a peak that's about 1/3 of the size of that, because the abundance of 37 is 1/3 of the size of that. I can read this off as 25%, and I can read this off as 75%. So I can get the abundance from the y-axis and the mass from the x-axis, and looking at where these peaks are. This is called a mass spectrum. It's useful for calculating average masses and that kind of thing. That's what we're going to do in a minute. But it's also useful as a fingerprint for a substance. So if you stick something like, say, an unknown sample of a hydrocarbon into the machine, it will produce a complicated set of peaks here, and that will fingerprint that substance. The computer that's attached to this thing can match that fingerprint up with a database and help you identify what compound you just put in there. So this is a very useful technique, mass spectroscopy. Let's use this mass spectrum to figure out what the average mass of chlorine should be. We're going to just do it very roughly. So I only have 2 significant digits on my masses and on my abundances that I'm reading off here. But my average mass will be the first abundance times the first mass plus the second abundance times the second mass. Okay, now let's stick the numbers in. The first abundance, well, let's see, for this peak, the abundance is 75%. Now I'm not going to put 75 there, right? I'm going to put the decimal number there. That is 75%, but I'm not going to write it as a 75% when I'm doing calculations with it. And then the mass of that same peak is 35U. And now I'm going to use the second abundance here. 0.25 is what 25% is, times the second mass, which is about 37U. So if I punch that into my calculator, it's going to come out to be 35.5U. Now, That's not too far off from what it says on the periodic table. Go look at what the average mass is on the periodic table. It's something like 35.453. This isn't far off from that. I'm not that close because I only had 2 significant digits with everything that I put in there. So I'm asking you in the problem below to look at a mass spectrum for an element and figure out what the average atomic mass of that element is. And you'll be able to tell which element it is if you look at the periodic table then.